So hello everyone. Welcome to the fourth live section of this course, which is quantum transport. I'm Gitanjali. I'm a PhD scholar from IIT Delhi, and I'm the TA for this course. So as I said before, in each live session, we will go through the contents that have been covered in week 4. And besides that, we'll try to solve the problems. Maybe it can be a numerical or it can be a conceptual one. So we'll solve both numerical as well as conceptual problem related to the concept that has been covered in week 4. So in the last week, we have started with quantum Hall effect. And in week 4, we basically see what are the different characteristics of quantum Hall effect and what are the different unusual phenomena that we can observe when we enter the quantum regime instead of a classical regime. So to start with, if you recall, for a free electron in a two-dimensional material, so we can write the energy as h cut square k square by 2m. K will have for 2D, you can write it as kx square plus ky square. Or if you consider 3D, you can write it as kz square. So for this, if you have this 2D material, then what will happen if we apply a transverse magnetic field in the, let's say we are applying it in the Z direction. This is one condition that we need to apply magnetic field in the transverse direction. That is the direction which is perpendicular to the electron flow or the current direction. And the second thing that we assume that the electron that are flowing through this 2D material, they undergo cyclotron motion without undergoing any collision. So that means no scattering event occur whenever the electron is undergoing a cyclotron motion. So we assume electron undergoes cyclotron motion without any without undergoing any collision. So for that case, if you apply a transverse magnetic field, we know that it will force a Lorentz force for the charge particle. So the charge particle will now deviate from its normal path. So they will try to circle around the in a plane which is perpendicular to the magnetic field. So because the electromagnetic field is in the z direction, so that means the kx ky component that we have seen earlier, they will be now dependent on each other because the electron is undergoing a cyclotron motion. So kx ky don't take any arbitrary value, so they will take a value that is satisfying the cyclotron motion. So EZ component, they will remain as it is because the magnetic force don't do any work in the direction parallel to the magnetic field. So it will remain as it is. But the energy that is perpendicular to the magnetic field, they will now become discretized. And we can borrow a concept from quantum mechanics. So we can write the energy that is in the xy plane. They will uh, quantize in form of the simple harmonic oscillator. So this is, we already know, so for simple harmonic oscillator, you can write the energy En is n plus half h cut omega c. So Kx, Ky, they are no longer independent. The cyclotron motion in xy plane, it will make Kx and Ky dependent on each other. So E perpendicular, we will have n plus half h cut omega c. Omega c is the cyclotron frequency. We can write it as omega c is Eb by m or m star. So now we will have total energy. For this case, it will be E parallel plus A perpendicular. Parallel will remain as it is. It is kz square by 2m. And the perpendicular energy, it will be discretized because of the cyclotron motion. So pictorially, if you want to understand what is happening to the energy level, so we can. So previously we had energies for 2D case. These are equally spaced in the 2 dimension. So this is the energy level in the absence of any magnetic field. So the dot points, these are allowed states that the electron will occupy. So now this is for the case where B is 0. So we are not applying any magnetic field. Now when we apply a magnetic field in the Z direction, so now the state will arrange in the form of Landau lengths. These are the Landau levels where we can see there will be allowed state in this Landau levels. Okay. So there will be states here. We'll see how we can calculate the number of states that is available in each Landau level in a area. So these are the Landau levels. And for this Landau level, the radius will remain constant for each case. We can find out the radius is kx square plus ky square. It will be k if, or let's say this is kr square. So kr will give the radius as well as what is the area occupied by each Landau levels. So to see the area that is occupied a Landau level. So we can do two types of quantization. One, we can see at the real space, as well as one, we can look at the momentum space. So momentum space will give what will happen to the energy, and in real space, we'll see some of the real phenomena like the uh, Subnikov oscillation. So we'll see it later. So let us go through what are the quantization conditions that we have seen in the K space. So for the K space, we have seen energy in the perpendicular direction. This is given by kx square plus ky square by 2m. And we can, from quantum mechanics, we can say this is n plus half h cut omega c. So to find out the area, we need the radius. For 2D case, this is cyclotron orbit. So it's like a circle. around a center. So that means if we know the area, then we can find out. If we know the radius, then we can find out what will be the area occupied by the uh, each Landau level. So Kn square, radius square, this will be 2 omega c by so h cut n plus r. So that means K in the radius of each Landau level in the K space is n plus half 2m omega c by h cut n plus half. So you can see these radius are quantized. So it don't take any arbitrary cyclotron radius. It need to satisfy this condition. So for the area, let's say we want to find out area of nth orbital in the K space, which is we can take area is in K space for the nth orbital. It is pi Kn square or 2m pi omega c by h cut n plus half. And if you put omega c Cb by m, so this will give m will cancel. So 2 pi Eb by h cut n plus half. So from this relation, you can find out many distinct properties of quantization in the K space, like the area, it is quantized, and if you take the area difference, so this is also, it is quantized. So let's say if you are taking the real difference between nth and n plus 1, so this will be 2 pi Eb by h cut. So this remains constant. So this is the quantization in the K space that we have seen in the lecture. Now for the real space, the energy that will take quantized energy, it is n plus half h cut omega c. So now as we are dealing with the real space, so we are dealing with the velocity. So this will be half m v square. In the momentum space, we have written the energy in terms of k, but in real space, we write energy in terms of velocity. And velocity, you can write it as omega r. So, so that means the radius of nth orbital in real space, it will be 2 h cut by m omega c n plus half. So from this, we can easily find out what will be the area. So area will be pi Rn square, which will be 2 pi h cut. And if you put omega c Cb by m, this is Eb n plus half. So in real space also, the area is also quantized. And from this, we can calculate one of the quantity that we're more interested during the experiment. So we can calculate the flux enclosed by any orbital in the real space. So flux, if you recall, no matter it is whether you are calculating the electric flux or the magnetic flux. So it is given by the dot product of the field with the area vector. So for magnetic flux, it is the dot product of the magnetic field with the area vector. This is the usual definition of flux. So we know what is the area occupied, and we know the B is in the Z direction and it has a magnitude of B. So this will give, if you put area here, this will give H by E n plus half. This is the flux quantization in the presence of strong magnetic field. And we also calculate what is the area difference between two orbitals in the real space, and it was coming around 2 pi h cut by E. So this is also constant for a given B. We have seen also that area difference in the K space, it was also constant, but it depends, it increases linearly with B. But now it is for the real space, it decreases linear inversely with respect to B. And if you take the dot product of the area difference in real space and the momentum space, it will come out as 4. So it is like a Heisenberg uncertainty relation that we can derive for this case. So this means if you have a closely spaced orbital in the real space, then in the momentum space it will be further apart. And if we have orbitals that is closely spaced in the momentum space, then the orbitals in the real space will be further apart. Okay. And this is all about what is the quantization in the real space as well as in the momentum space. Now we'll see what are for each energy level, each Landau level, what are the number of states that will be inside this each energy level for a given energy or in a area for a given area A. So for that, if you recall, density of states is nothing but the number of states per unit area per unit energy. So if we know the density of states, then we'll be able to calculate what is the number of states that will be there inside a given Landau level. So let us say we want to find out the number of states per unit energy in an area S. We want to calculate the states per unit energy in an area. Yes. So for that, we need to know what is the density of states of this 2D system, because quantum Hall effect we mostly see in the 2D system. In 3D, we won't be able to see it because there will be scattering component. So for that is why we are more interested in the 2D system. So for this, we to find out the number of state, we need to know what is the number of density of states for the 2D. And we can multiply it with the area where we want to find out the number of states. And besides that, there is a factor of spin degeneracy. So like if for each energy level, there is spin up and spin down, they can occupy the same energy level, then we can say for each state there are two particle that is occupying that states. So that is why we multiply it with the degeneracy, and for electron it is 2. So, and if you recall for the 2D case, for 3D case, density of state, it is varying a square root of E, right? But for the 2D case, it is constant. And the constant factor is m by 2 pi h cut squared. So this is the expression for density of state for the 2D case. And we can multiply it with the area vector where we want to find out the number of states. So this is for number of states per unit energy. Now, if you want to find out number of states in each Landau level. So for that, what we want to find out is number of states in, let's say, one Landau level within the area S or A. So for that, we need to multiply whatever we have got here with the what is the energy width of one Landau label. So, and if you recall, each Landau label, they are separated by an energy h got omega c. So what I mean is, if you recall the lecture, we have a schematic like this. So density of state there for the quantum Hall effect, they are like a delta function. And these states are separated by h got omega c. So that is why if you want to find out number of state in each energy level, so we can multiply it with h got omega c. And this will give, if I'm not wrong, Gs phi by phi 0. So phi 0 is the quantum of magnetic flux, it is h by E, and phi is the magnetic flux through this area S. So this is how we can calculate the number of states in each Landau level within an area A. So we know what are the number of states inside this inside each Landau level. Now we want to find out for a given condition, for a given magnetic field, what is the number of Landau level that will be occupied and what are the Landau level that won't be occupied. Because that will give whether the device is in the plateau region or whether it show the Subnikov deassociation. So for that, we can calculate this if we calculate the filling factor. So filling factor is nothing but it says it will give us how many Landau labels will be occupied for a given magnetic field and for a given electron density. So to calculate the filling factor, so this is given by the ratio of electron density, which is nothing but the areal electron density, number of electrons per unit area, divided by what is the number of states available in each Landau label per unit area. So we are basically dividing the number of electrons that is available by the number of available states in each Landau. So let us say electron density is Ns and number of states in each Landau level. This is nothing but Gs, h got omega c, and density of states of the 2D system. Gs. For 2D, the density of state is 2 pi m by 2 pi h got square, h got omega c. If you simplify it, this will give Ns Gs Eb by h. And if you're considering the particles are electrons, then the spin degeneracy will be 2. This will be 2 Eb by h. And for the case where the spin degeneracy is lifted, like there is a G-man splitting. So for that case, this factor will be 1. So each state will be occupied by one electron. The spin up and spin down, they will split further if the Zeeman splitting is it is significant. Okay. Otherwise, if the question says it is spin degenerate, then you can take 2 EB by H. But if it says the spin degeneracy is lifted off, you should take NS by EB by H. Okay. So this is about what are the number of states that will be available for a number of Landau level available for a given magnetic field. Now we will see what will happen when we increase the magnetic field gradually from low to high. So for that case, if you recall the figure, for a classical case, if you recall the voltage, Hall voltage, it is a linear function of uh, the magnetic field. Also, the resistance, it is also a linear function. If you recall, Rxx is given by B by N. So this is for the case where we have the low magnetic field. So for low magnetic field, the scattering will happen. So because of the scattering, it will be linear function of B. But when we apply a strong magnetic field, the scattering will be suppressed. And we will see quantization in terms of the Landau level in presence of a strong magnetic field. So for that case, if you recall the figures, for the voltage that is along the, sorry, what the resistance along the direction of current, it shows a oscillatory behavior. And also for the Hall resistivity, so linear in the low regime, but gradually it shows a, so let me draw it separately. So it will be linear, then it's so a plateau, then it will increase, then so it's so a state, it increases in a step-like manner. So we'll see what is happening here, what is happening in this regime. Okay. So when we increase the magnetic field, so that means if you recall, increasing the magnetic field means decreasing the filling factor. So nu is directly proportional to, it is inversely proportional to 1 by B. So if you increase B, that means nu will decrease. So that means more, the number of levels, Landau level occupied will now decrease. So let's say initially we have the Landau level that is occupied below the Fermi level. This is for the case B equal to 0. For this case, when B is 0, what will be Rxx? Rxx will be B by Ne. And Rxy will be 0 because there is no magnetic field. Now, when we gradually increase the magnetic field, this Landau level will move because the filling factor is now decreasing. Also, the area of each Landau level will also increase. So that means each Landau level will now occupy more states as compared to the states that we have before in the low magnetic field. So when this Landau level move across this Fermi level, what will happen? So whatever transport that we are seeing, we are more uh, the transport are occurring around the Fermi level. So we are more interested in what is happening around this Fermi level, whether there are unoccupied states around the Fermi level or not. If they are unoccupied state, then there will be a transition, and we'll see a resistance along the direction of the current. But if there is no energy level that is occupied, that is empty or partially occupied, then in that case, we'll see a plateau region. So what I mean is that when this level uh, goes through this Fermi level, let's say it comes to here. So for that case, some of the states will be empty and some of the states will be occupied. So what will happen now? We'll see a Rx of which is not equal to 0, because this is what we call the SDS oscillation. So in the diagram, we'll see these peaks whenever the Landau level crosses this Fermi level. But once this Landau level fully cross this Fermi level, that means, let's say now we have two levels that is below the Fermi level and it is fully occupied. For this case, we can see there are no states around this Fermi energy. There are no bulk states that is present around this Fermi energy. So that means now this will become 0. So there will be no resistance along the direction of the current. So the bulk will become insulating. So whatever current that will flow, it will flow through this through the edges of the sample. Because for the edges, if you recall the graph, uh, in the real space, we can draw the Landau levels like this. So even though, let's say Fermi level is around here, so there is a gap between the bulk state to the Fermi level. So that is why the bulk will become insulating. There is no allowed state to conduct along the direction of the current. So bulk will become insulating. But at the edges, the energy is quite different to the energy what we have in the bulk. So in the edges, this energies, this state will cross the Fermi level. So based on the number of Landau levels that is available, we'll see age states around the edges of the sample. So let's say this is the sample, we'll see current propagation along the edges, not in the bulk. So this is what it means physically when we increase the magnetic field. So that is why we see for the Hall resistance, for the low regime, it is like linear. But once it crosses a critical value, so it will attain a plateau region, then it will suddenly increase, then plateau region, then will suddenly increase, then a plateau region. So plateau region is the region where the bulk is insulated. There is no extended state through the bulk. And the second is whatever the conduction is happening, it is through the A states. So we'll see a non-zero resistivity for the Hall for the in the transverse direction. It is given as number of 8 states into E square by H. We'll see further. And this is for the plateau region where the conduction is happening through the A state. Also, we'll see that for this plateau region, the resistivity along the current direction will be 0 because the bulk is insulating. So this plateau region is the region where Rxx also goes to 0. And if we look at this region where the transition is happening, this is the region where the Fermi level, the Landau level is passing through a Fermi level. So that means there are unoccupied states. So bulk will now become conducting. So because in this case the bulk will become conducting, we'll see a rise in the longitudinal resistivity. That is the resistivity along the direction of current. And there will be no, so this is also the SDS oscillation. So this is what we mean, this is how we can understand this graph. There is a question. So you are asking about quantum Hall effect can be explained by one-dimensional transport formalism or two-dimensional transport formalism. Which one we'll see in the quantum Hall? So quantum Hall effect basically means the conduction of a state. And eight states are nothing but these are the states that is localized around the uh, edges of the sample. And if you recall, these A states are, if we recall the lecture, the counter propagating A state, they are spatially separated. So we have only one directional A state. There is no bidirectional A state. So that means you can now guess whether quantum Hall effect it is one-dimensional transport or two-dimensional transport. Okay, let us move to our next part. So this is all about how we can understand the graph that we have seen in the lecture. In the sum of the cases, we'll see Rx is 0. In the sum of the cases, we won't see Rx is non-zero. Okay, now let us see how we can calculate the uh, number of electron density in a given sample. So for that case, let us say we apply a magnetic field and we change the Fermi vector from 3 to 2. So we increase the magnetic field such that only previously only 3 Landau level are occupying below the Fermi level. Now we have 2 for Landau level that is below the Fermi level and these are occupied. So if you experimentally have this information, so that means if you take the difference of this will be 1, right? And for fill-in factor, you can recall this is Ns by 2E B1 by H minus Ns by 2E B2 by H. This must be 1. Or we can write Ns H by 2E delta 1 by B should be 1. Ns is 2E by H delta 1 by B. So this says that we can easily calculate the electron density if we know the magnetic field variation for a given sample. And also we've seen the magnetic length. LB. This is given by root over H cut by EB, I think. So this is the, this will give the spatial extent of the wave function in the lower energy. Okay. Okay, so I think we are almost done with the concept. One thing we were left with is that for the A states, we have, for example, we have bulk states as well as the A state. A state will occur in the plateau region and the bulk state will see in the SDS oscillation. For the bulk state, we can write the energy of the Landau level as n plus h got omega c. But if you look at the edges, for the edges, these are confined. So in the edges, we have asymmetry, right? So there will be a increase in energy because of the confinement. So for the edges, the energy would be n plus half h squared omega c plus the confinement energy plus the energy that is driving it uh, along the channel. And as I have said before, because of this change in energy, if you look at the energy diagram, in the edges, the energy, the Landau level will cross the Fermi energy. So even though we don't have any bulk states for a given magnetic field, we'll see a state which is propagating along the edges of the sample. And to find out the number of A state, we just need to calculate what is the filling factor. So filling factor, if you recall, this is nothing but what are the number of occupied Landau labels. So it will give the number of mm, occupied Landau level. And if you know the filling factor, that will give the occupied Landau level, and this for each occupied Landau level, we will have one A states. So that means number of A states will be equal to the number of Landau level that is occupied. Think. And we can calculate what is the conductance of this A state. This is given by Gs and A square by H. This is the two-terminal conductance. Resistance plateaus in the quantum Hall effect occurs when okay. Okay. Listen, I think you are asking me the answer to the assignment, right? Uh, So for now, I won't be able to clarify the doubts that you must be having for the assignment because it will give you the answer directly. So only I will be able to clarify the concept as far as I can. But for me, it won't be possible because the deadline is not over. So I will be able to clarify your doubts after the deadline, not before the deadline. So one thing I can say is that if you recall, the first question is I have already covered. Resistance plateau I have already covered. Just go through the concept, you will be able to pinpoint what will be the answer. It is quite easy. If you know the concept, then you will be able to see what will be the answer. No one is answering in Q&A. Okay, so if you have any, so for what I am saying is that it's not possible for me to directly say you the answer. But in the question, if you have any doubts, then I will be able to clarify that doubt, but not the answer directly. And let's say you think the question there is something missing in the question, that is one of the parameter is not given. If you think, then please write it in the Q&A, because I think the NPTEL team will answer if you have the query to that question before the deadline. So what I can suggest is that just go through the lecture content. Okay. So it's not like the questions are quite difficult, but if you go through the lecture content, then you can see most of the question, the answer is already there in the lecture. So just revise the lecture, or uh, we are now in week 4, so I'm also going through the same concept. I'm also trying to explain the same concept. So go listen to my concept, listen to whatever I am explaining. And if you have doubt in that, then please free to ask me. So I will try to clarify doubt as much as possible. So let me, for your sake, let me revisit uh, the concept that can help you to go through help you to solve the assignment. Okay, so we are saying what will happen when we increase the magnetic field. And marks are also given less for assignment 3. So problem is there for scoring in assignment. Marks are given less. I didn't get it. Can you please clarify it further? What do you mean marks are less? Let me see what was the assignment 3. So if you think that your answer is correct and whatever answer is given, if you have doubt in that answer, then I would suggest, so just attach your answer to your detailed answer to that question. So write down the question or attach the question, then write down the way you are solving it and how you are getting that answer. So write down, attach this detailed answer in the mail, and raise the question in the Google group. Okay, in the Q&A group. So if you do that way, then it would be easy for the NPTEL team to see whether the answer was wrong, or whether you are wrong somewhere. So if you just say I'm getting this, but the answer is this, then it won't be possible to track which one of you is wrong, right? So just attach the detailed solution in the mail and ask whatever doubts you have. Okay, if no one is answering, then I will try to talk to the NPTEL team. I will wrote to them. I will ask them that the students have doubt in the question. Let's see whether they are able to. So don't worry. If your answer is correct, then they will update the answer if they think your answer is correct, and they will update your marks also. So it's not like it's final mark. So if they think the answer for your case is correct, then they will update the marks as well as the answer. But the main thing I would like to suggest is that whenever you are asking the question that you are getting this answer, but the answer is given this, it's a better practice if you attach your solution to that mail, because for that case they can track down what how you are solving it, and whether you're solving whether the steps are correct or not. So attach the solution for each doubts that you have. Okay. And in the meantime, I will wrote to them that the students have doubt, and let me see whether I'm getting any response on it. Okay. So what we were, so we, let's see this graph once again. So in the quantum Hall effect, we have a graph like, for the Hall resistivity, we have a graph like. So there is a linear region for the low magnetic field. Now we'll see a plateau region, then there is an increase, then plateau region, there is an increase, then the plateau region, then also there is increase. So the resistivity, the Hall resistivity, it increases in a step-like manner. And what I've said earlier is that in the plateau region, that is the resistant plateau region, this is the reason where the bulk become insulating, because in this case, the energy levels are fully occupied. There is no energy level that is near to the Fermi level that can excite to the next Landau level. So for this plateau region, the bulk become insulating. There is no conductance along the direction of the current. So in the picture, there is no conductance. So let's say the current is in this direction. Conductance through the bulk will be forbidden. Only the conductance through the edges will be there. So that is why we say bulk is insulating. And there will be a state which is a conductivity conductance of, which is given by E square by H multiplied by the number of A state that is available. And for the reason where we see this increase, so this is the reason where one Landau label is crossing the Fermi label. So there are available states where the electron can excite. So for this reason, we'll see a peak in the longitudinal resistivity. So let me show clearly. So we have two reasons. One is plateau reason, and one is the reason where it is increasing. Let's say it is increasing linearly. In the plateau reason, the conductance only happens. This is the current direction. So there won't be any conductance along the bulk. There will be conductance along the only along the edges. But in the linear region, we will be able to see a conductance along the edges, along the bulk of the sun. So that is why we will see a SGS oscillation in the graph. And for this case, we'll see a flat Hall resistivity. So this is in brief what I wanted to say. Okay, so now we are almost done with the concept. Now let us solve few problems. But before that, let us see what are the problems that we haven't solved in the last lecture. Okay, so we are, there is a question. Mapping of Fermi surface is done exploiting Subnikov-Diaz effect or Diaz-Farnham effect. I'm confused in this. So, you just need to look into the core concept. What is Subnikov-Diaz effect and what is Diaz-Van Alphen effect? So, if you recall, Subnikov-Diaz effect is nothing but it is the oscillation in the uh, longitudinal resistivity or conductivity, the presence of a transverse magnetic field. And the Diaz-Van effect, it is the oscillation in magnetic susceptibility in the mostly in the metal. So just see which one of these will give the mapping of Fermi surface. Okay, now let us solve the problem. We'll try to solve few numerical as well as conceptual problem related to the concept of Big Four, and it will also help you to solve the assignment. But the questions are not like they are direct question, but if you go through the question, then you will be able to solve the assignment. Okay, so our first question is in a high mobility 2D electron gas, the Hall resistance is measured to be is given RH is 12906. Then what is the filling factor nu? I will give you some time to solve it. Please try to solve it and let me know the answer. Recall the concept of week 3. What is the relation between the uh, filling factor and the Hall resistance? Then you will be able to find the filling factor. Okay. Okay. So you are getting an answer up to good. So I think you are you know the concept. So you must have used RH is 1 by nu, H by E square. H by E square, this value is already known. This is 25.813 ohm. So that means nu is 25.813 ohm by March. RH is given, it is 12906. So this will give 2. Okay, so for the next one, it is also a conceptual question. Estimate the longitudinal or resistivity RXS when the charge carriers occupy the plateau level with I equal to 1 in a gallium arsenide two-dimensional electron gas system. Given RXY is 4000 ohm. So you need to calculate what is RXX. First answer is 2000 ohm, second answer is 1000 ohm, third is 0 ohm, or it cannot be determined from the given data. Yes, so this will be 0. It is quite straightforward because RXS is in the, it is saying the carriers are in the plateau region. So for the plateau region, the RX is 0 because there is no ball conductance. Next question. The fractional quantum Hall effect differs fundamentally from the integer quantum Hall effect because fractional quantum Hall effect occurs at higher magnetic field, or fractional quantum Hall effect requires formation of new state of matter with fractionally charged quasi-particle, or fractional quantum Hall effect is less precise in its quantization, or option D, fractional quantum Hall effect doesn't exhibit vanishing longitudinal resistance. Option D. No, it's not correct. So it will be able, we will be able to see vanishing longitudinal resistance even in the fractional quantum Hall effect. But fractional quantum Hall effect, if you recall the integer quantum Hall effect, this is like a single electron pages. But when we say fractional quantum Hall effect, there is strong electron interaction which leads to the fractional quantum Hall effect. So that means fractional quantum Hall effect requires formation of new state of matter with fractionally charged quasi-particle. So answer would be option B. Okay, so we are done with week 3. Now we'll start solving problems related to week 4. Question number 1. The Landau level energies for a two-dimensional electron gas in a magnetic field are given by n plus half h got omega c, where omega c is Eb by m. Which statement best describe how the density of state versus the energy looks like in the ideal, which is no disorder or zero magnetic field, zero temperature case? Whether it is a constant density of state independent of energy, or option B, an exponentially decay of density of state at high energy, or option C, a set of equally spaced delta function fixed at each Landau level energy, or option D, a continuous linear increase of density of states with energy. Option C. Yes, it's correct. Question number 2. Consider a sample of area. It is given 10 to the minus 8 meters square. In a magnetic field, B is 5 Tesla. How many states are available in a single Landau level, assuming spin degeneracy is elliptic? So number of states available in a single Landau level. Not getting. So let me solve it. Okay, so number of states available in a single Landau level. This, if you recall, it is given by spin degeneracy EB by H. And it's given spin degeneracy is elliptic. That means GS is now not 2, it is 1. So when the spin degeneracy is elliptic, we can write it is EB by H. All these values are given. E is 1.6 into 10 to the minus 19. B is 5 Tesla. And okay, there will be area, right? You have to multiply it with the area. Area is 10 to the minus 8. And H is 6.63 into 10 to the minus 30. So this will give 1.2 to 10 to the power 7. So this is approximately 12 million states per energy level, per Landau level. Option A. Just let me know if you think the answer is not correct or if you have any doubt in the steps. Okay, question number 3. Consider a Hall bar of geometry in the quantum Hall regime with filling factor nu equal to 2. How many chiral edge states carry current along each edge and what is the corresponding Hall conductance? Whether there are 2 H channels per edge and sigma xi is 2 e square by h, or it is 4 H channels per edge with sigma xi 4 e square by h, 1 is channel per h with sigma xi e square by h, or there is no h channel, but sigma xi is 2 e square by h due to bulk conduction. Option B. I doubt it's not correct because it's given nu equal to 2, right? So nu equal to 2 means the filling factor is 2. So that means 2 Landau levels are completely occupied. And if these two are completely occupied, and if you recall at the edges, this Landau level cross the Fermi energy. So that means each Landau level will cross the Fermi energy across the edge. So the A states will be equal to the filling factor or the number of Landau levels that are fully occupied. So it will be 2 and the conductance will be 2 into E square by H. Answer is A. Okay, next question. For a given two-dimensional electron gas and fixed magnetic field, which experimental knob most directly changes the filling factor nu and can be used to move between different quantum Hall plateaus? Whether by changing the sample temperature, it's possible to move between the plateaus, or varying the sample length along the current direction, tuning the gate voltage to change the number density, or rotating the sample around the magnetic field axis. Which of these following uh, will give a experimental factor to move between two different quantum Hall plateaus? Option B, varying the sample length along the current direction. So it's not correct. Uh, Varying the sample length along the current direction, it won't give the changing the plateau level, moving between the different plateau levels, right? So to move between the different plateau levels, that means we are changing the filling factor. So nu is Ns by 2 EV by H. And for a given magnetic field, the filling factor is directly proportional to the electron density. So if somehow we can change the electron density, which is by means of changing the gate voltage, so that means we can make more Landau levels that will we can change the positioning of the Landau level. And by changing the position of this Landau level, we have seen that when the Landau levels moves across the Fermi energy, it's possible to get excitation from one plateau level to the other plateau level. So what I mean is that in the graph, we have seen like this, right? And the to go from this plateau level to this plateau level, for a given magnetic field. So we are keeping the magnetic field constant. So only factor we have is the number density. And if we change it, that means the filling factor will change. So the Landau levels will now move across the Fermi level, and when it crosses the Fermi level, then we'll see excitation. I think the option will be, answer will be option C. Question number 5. A two-dimensional electron gas at zero temperature is in a strong magnetic field such that the filling factor is nu is 1.5. Assuming liptate spin degeneracy, which of these following best describes the occupation of Landau level? So when it says nu is 1.5, then whether the lowest Landau level is empty and the second one is 1.5 times filled, or the Landau level is half filled, the second one is empty. Both the lowest and second Landau levels are three-quarter filled, or the lowest Landau level is full and the second one is half. Which one of this you think is giving what do we mean by nu is 1.5? So when nu is 1.5, you can easily guess. So nu is 1.5 means the lowest Landau level is filled, and the second one it is half filled. So this is how we can interpret whatever value we are getting for the filling factor. So if it was 1, then the lowest Landau level is fully occupied. And if it is 2, then the two Landau levels are fully occupied. If it is 2.5, then two Landau levels are occupied, and the third level is half occupied. So the answer to this is uh, the lowest Landau level is full, and the second one is half filled. Please provide recording of the session. So the recording, if you see the course website, so there is a link to this. There will be link to the Google Sheet, and in that Google Sheet, I upload the link to this recording session. So from that, you can get the YouTube link. I will try to upload it by tomorrow. We will and try to update the Google Sheet, and from that you can revisit the session. Okay. In the left panel, you can see there will be a tab to problem solving session. In that tab, there will be a link to the Google Sheet, and in the Google Sheet, I upload the link to the YouTube link to the session. So the other information. Do you have any other doubt? Okay. So let us move to our next question. So it's given a two-dimensional electron gas density of 4 into 10 to the power 15 per meter square. At a magnetic field B1, the system is at a filling factor nu equal to 4. At what magnetic field B2 that the filling factor will become 2. We have seen earlier, if we increase the magnetic field, then the filling factor will decrease. So that means the answer to this question will be B2 will be higher than B1. Now to know the exact relation between B2 and B1, you need to know what is the relation between the filling factor and the magnetic field. Can you please solve it quickly and let me know the answer? Given the electron density is same and there is a liptate spin degeneracy, that means GS is 1. Option B, good, it's correct. So nu is inversely proportional to B. So that means nu2 by nu1 is B1 by 2. And B2 will be, sorry, nu1 by nu2 B1. Nu1 is 4, nu2 is 2. Is 2 times of B1. Question number 7. For a two-dimensional electron gas with effective mass m star and the cyclotron frequency omega c is Eb by m star, it's given we are decreasing the effective mass. Effective mass is reduced while keeping the B fixed. Then how do the Landau label spacing and the density of state structure will change? So what is the effect of decreasing the effective mass on density of states and the energy spacing? If we keep B constant, but we are changing the cyclotron frequency. Option A, Landau levels move further apart and DOS peaks become more widely spaced in energy. Option B, Landau levels move closer together and DOS peak becomes denser in energy. Option C, Landau levels and the density of state structure are not changed. And option D, Landau level disappear and the density of states become that of a free 2D gas. Which one of these you think is the correct option? When we decrease m star, but we are keeping B fixed. Good, it's correct. Landau level. So energy spacing, it is h cut omega c. So this is h cut Eb by m star. So when we decrease m, so delta will now increase. And when the delta E increase, the density of state now peak more. They will widely separated in energy because delta is increasing. So answer is option A. Question number 8. A two-dimensional electron gas in a magnetic field has a Landau levels broadened by disorder into Lorentzian shape of width gamma. So it says there is a spreading because of the disorder. Okay. Qualitatively, how does increasing gamma affect the visibility of Subnikov-Diaz oscillation in the longitudinal resistivity as a function of 1 by B? Larger gamma increases the amplitude of SDS oscillation. Larger gamma shifts the oscillation period in 1 by B but leaves the amplitude unchanged. Gamma does not affect SDS oscillation at all. Or option D, larger gamma decreases the amplitude and can eventually wash out the SDS oscillation. So there we are introducing more disorder into the system, and because of the disorder, the Landau labels are now spreading out. So the density of states will now spread. Then according to you, what do you think when we increase the disorder, what will happen to the SDS oscillation? Option A. So let us see in the detail and let me know if we have any doubt. So Subnikov-Diaz oscillation, it is related to the oscillation in the uh, conductivity or resistivity along the direction of the current, right? So when the Landau levels broaden due to disorder, that means the sharp peak that we're seeing in the density of states, they will eventually smear out. So they will spread out like this. So the density of states will become wider and they will, and for the adjacent energy level, they will now overlap. So that means if now they are overlapping with each other, that means there is a possibility of scattering in the system. And this scattering will decrease it will decrease the amplitude, as well as it may be possible that the SDS oscillation will be vanish. Okay, so what I mean is, let's say in the energy scale. So if you recall this density of states, we have like this. They peak out at the discrete energy level of n plus half h cut omega. And they are separated by a value h cut omega c. Let us say gamma is much, much less than h cut omega c. So gamma is very small. So that means the Landau levels, they will be well separated. So because of this well separation, there will be a strong oscillation in the density of state and there will be a clear SDS oscillation. Because SDS oscillation occurs whenever there is a increase in the increase in the bulk resistivity along the direction of the current because of the quantized energy level. Now, let us say it is in the range of h cut omega c. So now the Landau levels will now, they will start overlapping. So if they now start overlapping, so that means there will be the density of states modulation that we have seen earlier, that is the peak. They will decrease and they will try to overlap and the oscillation will become smaller. And when the gamma is much, much greater than omega c, now it's like a continuous state. So there is no discretization in the density of state. And because of this uniform density of states, what will happen to the resistivity? It will be like a classical resin, like it will be like a B by N. So it won't show any oscillatory behavior. Resistance will be there. Resistance will be there, but there won't be any oscillation. So it will be like a constant with respect to the magnetic field. So that is why we say whenever we want to see the quantum Hall effect, then this broadening that happens because of any disorder or because of increase in temperature or because of any scattering. So that should be less than the time which is required for one cyclotron motion. Okay. So that is why we say that this time period should be less than that. So I hope I'm clear to the concept. If not, let me know once. I will try to clarify the concept once again. Okay, question number 9. there is a two-dimensional electron gas, which is areal electron density of 3 into 10 to the power 15 per meter square. In a magnetic field such that the degeneracy per Landau level is GB is given 1.5 into 10 to the power 50. So degeneracy per Landau level means the number of states that is available in each Landau level per unit area. Now it is asking about what is the filling factor. Can you calculate it quickly and let me know the answer? It's also given, assume that the spin degeneracy is fully lifted. Means GS is 1. You don't need to take GS is 2. So you mean you are getting nu equal to 1 or you are referring to option A? If you are referring to option A, then this is correct. Nu will be 2 because nu is nothing but Ns by Gb. So this is 3, this is 1.5. So what does this mean? This means two Landau levels are completely filled. And what will be the number of A state? Number of A state will be 2 per boundary. In each boundary, we'll see 2 A state. And conductance, you can calculate it eventually. Okay, consider a 2D electron with parabolic dispersion in a magnetic field. If the energy of the nth Landau level is En is n plus half h cut omega c, what does the equal spacing, that is delta is h cut omega c, directly imply about the spacing of the cyclotron orbit radii in the momentum space? Option A, whether the square of the radii in momentum space are equally spaced, so the area between the rings is constant. Option B, the radii shrink with increasing n, causing the area between rings to decrease. Option C, radii in momentum space are equally spaced, forming concentric ring with constant radial separation. Option D, radii in real space are quantized deeply, while momentum space radii are continuous. So it is basically asking you about what is the quantization condition in real space and in the momentum space. So if you recall the quantization condition, the k perpendicular square in the real space, in the momentum space, it is given by 2 omega by c h quart n plus r. So that means k square n plus 1 minus k n square. It is 2 n omega c by h quart. And from this, you can easily find out the area of the difference in area. This is 2m pi omega c by h. So this means that the square of the radii in momentum space, they are equally spaced because these are constant, and the area between the rings is also constant. Option A. For a given magnetic field, B is 10 Tesla. What is the magnetic length LB? B is given 10 Tesla. What is the magnetic length? This is direct formula based. Eighty-one. 8.1. I think that's what you mean, right? Okay, so you're meaning A. So that option 81 and 8.1. If you recall, LB is H cot by EV. This is H cot is 1.055 10 to the minus 34. E is 1.6 10 to the minus 19. B is 10 Tesla. From this, I think you will get 8.1. Let me check. Yes, H cot, you can calculate it. H value, you know, it is 6.63 into 10 to the minus 34 joule second. H cot is nothing but H by 2 pi. So if you divide it by 2 pi, then you will get 1.055 into 10 to the minus 34. So I think this will give 8.1 nanometer. So check it once again. Okay. Question number 12. In a two-dimensional electron gas under perpendicular magnetic field, what is the most appropriate physical interpretation of magnetic length LB? Whether magnetic field LB refers to the characteristics radius of electron cyclotron orbits in a given Landau level, or it refers to the mean free path of electrons between impurity scattering, or it refers to the scanning length of Coulomb interaction between electrons, or it refers to the spatial extent of the entire quantum Hall sample. What does LB means in the physical picture? It's option A. It's the characteristics radius of electron cyclotron orbit in a given undoubted. Question number 13. We have an experimentalist observed that the electron density equals to the Landau level degeneracy per unit area at a certain magnetic field. In terms of filling factor, what does this imply? Whether nu is half, or nu is 0, or nu is 1, or nu is 2. Landau level degeneracy means the number of states that are available in a given per unit area. You will get it. Nu is 1, I think, because it's given electron density is equal to the Landau level degeneracy. So nu is 1. So what will be conductivity? Hall conductance for this case, and what is the number of wasted that you will get it here? Nu is 1, so number of wasted will be 1, and the conductivity will be E square by H. If we ignore the spin degeneracy, it will be E square by H. Okay. Question number 14. At a fixed electron density, increasing the magnetic field causes the filling factor nu to decrease. Which statement best explain this in terms of the magnetic length? Increasing B decreases LB, so there are fewer states per unit area. Increasing B leaves LB unchanged, but changes the spin degeneracy. Increasing B decreases LB, so there are more states per unit area. Option D, increasing B makes LB imaginary, suppressing the conduction. At a fixed NS, when we increase the B, nu decreases. What is the effect on LB? When you increase B? Okay. So for this, if you recall, LB is H cut by EB, right? So we want to find out what is happening to LB and what is happening to the number of states per unit area. So number of states per unit area. This is spin degeneracy, density of states, and energy of one Landau level. So this is GC EB by H, or GS 2 pi LB square. So when you increase B, that means the magnetic length will now decrease. And the magnetic length is decreasing, that means the number of states will now increase. Okay. Or you can uh, mm, you can guess what will happen to the number of state from the filling factor. because now the filling factor is decreasing. And if you recall, when the filling factor decreases and when we increase the B, the energy area of the energy state in the K space will increase. That means more states will now occupy the lower energy level. So that means each Landau level will now occupy more uh, energy state because we are increasing the magnetic field B. So it will decrease LB, but there are more states per unit area. Option C. Question number 15. You measure the SDS oscillation and find the successive minima occur at 1 by base 0.5 Tesla inverse and 1 by B 0.56 Tesla inverse. Assuming spin degenerate Landau level in a single 2D subband, estimate the seat density. What is NS? So we are changing magnetic field. So that means we are changing the filling factor. And it's that these values, they are occurring at successive minima. Minima of the density of states. So what is NS according to? Let me give you this as a homework. Take the question, try to revisit the concept, and let me know what is the answer you are getting. Okay. So it's given there are two SDS oscillation and the distance between uh, successive minima. It is occurring at one value 0.5 Tesla inverse, one value is 0.56 Tesla inverse. Then from this, what is the electron density or sheet density? Okay. So we are done for today. Let me know whether you have any query. In the Google Sheet, there are YouTube links for week 1 to 3. Are these links to the record? Yes, these are the links to the recording session. So the videos are they are in public. So if you have the link, you can see the videos. You can revisit the sessions. Okay. Let me know whether you have any other doubt. I will write to the NPTEL team about your query that you are not getting any response. Or as I suggested, please try to attach your solution for that given problem if you are not able to get it. And try to ask your doubt in the Q&A session. And if you have conceptual doubt, you can ask me here. But for the uh, question that are floated in the assignment, it's better to ask in the Q&A because there will be a track that you are asking the question and they will see it and will try to address your question. Okay. So we'll stop for today. Thank you for joining the session. In the next live session, we'll try to solve few more problems of week 4 as well as week 5. And we'll see, we'll meet on next Friday, same time from 6 to 8. So for now, thank you for joining the session. Bye everyone.